Well, a little late to this, but let's read the Qwen3 VL technical report. I really like this model, so let's just relax today and read about Qwen3 VL. The Qwen3 VL technical report. Abstract. We introduced Qwen3 VL, the most capable vision language model in the Qwen series to date, achieving superior performance across a broad range of multimodal benchmarks. It natively supports interleaved context of up to 256K tokens, seamlessly integrating text, images, and video. The model family includes both dense 2B, 4B, 8B, and 32B, and mixture of experts 30B, A3B, and 235B and A22B variants to accommodate diverse latency and quality trade-offs. So dense models is just basically all parameters are active, whereas with the mixture of experts, you have 30 billion parameters available, but 3 billion parameters are active, and then the bigger one has 235 billion parameters total, but then 22 billion parameters are active per generation. Okay, let's see. Hopefully I stopped flickering. Okay, yeah, so Qwen3VL delivers three core pillars. Uh, First, markedly stronger pure text understanding, surpassing Qwen3VL delivers three core pillars. First is a markedly stronger pure text understanding, surpassing comparable text-only backbones in several cases. Second, robust long context comprehension with a native 256K token window for both text and interleaved multimodal inputs, enabling faithful retention, retrieval, and cross-referencing across long documents and videos. And finally, advanced multimodal reasoning across single image, multi-image, and video tasks, demonstrating leading performance on comprehensive evaluations such as MMMU and visual math benchmarks, Math Vista, and Math Vision. So they're saying that, okay, first, the Qwen3 VL models are actually stronger than the regular Qwen3 text models. So that's a surprise. Well, not really. It is newer, but same model architecture. And then the second one is you have a 256K token context window in combination for both text and the image and video parts of it. And then finally, you have support for single image, multi-image, and video inputs. So yeah, it's good. Okay, architecturally, we introduced three key upgrades. First, an enhanced interleaved MROPE for stronger spatial temporal modeling across images and videos. Two, deep stack integration, which effectively leverages multi-level vision transformers (VIT) features to tighten vision language alignment. And three, text-based time alignment for video, evolving from TROPE to explicit textual timestamp alignment for more precise temporal grounding. To balance text-only and multimodal learning objectives, we apply square root reweighting, which boosts multimodal performance without compromising text capabilities. We extend pre-training to a context length of 256K tokens and bifurcate post-training into non-thinking and thinking variants to address distinct application requirements. Furthermore, we allocate additional compute resources to post-training phase to further enhance model performance. Under comparable token budgets and latency constraints, Qwen3VL achieves superior performance in both dense and mixture of experts architectures. We envision Qwen3VL serving as a foundational engine for image-grounded reasoning, agentic decision-making, and multimodal code intelligence in real-world workflows. So I don't really like these graphs, but it's really hard to tell. But at the time, it's showing superior performance in various benchmarks in comparison to things like Gemini 2.5 Pro, Claude Opus 4.1, DeepSeek, even like the old Qwen for like text-related things, and even GPT-5. And then for the vision part of it, so in comparison, I think like Math Vista, Math Vision, I think MMSR, I think these are all vision based. you have it be compared to Gemini 2.5, for instance, being superior and GPT-5 being superior. I don't understand how this Qwen3 A22B thinking is in here though, because um, it's not vision. So I'm not sure if all like some of these aren't vision, I guess. If we take a look at it, right? So like these only I think only this one has it. So AIM 25. Regardless, it's good at the time. But now we have newer models, so I think things have caught up since then. So introduction. Vision language models, VLM, have achieved substantive progress in recent years, evolving from foundational visual perception to advanced multimodal reasoning across images and video. The rapid advancement of VLMs have given rise to a rapidly expanding landscape of downstream applications, such as long context understanding, STEM reasoning, GUI comprehension and interaction, and agentic workflows. Crucially, these advances must not erode the underlying large language models or LLMs' linguistic proficiency. Multimodal models are expected to match or surpass their text-only counterparts on language benchmarks. And I think this is a challenge when you're creating a VLM, is that you have to be good at multimodal, so images and video inputs, but at the same time, you cannot regress or degrade the LLM aspect of it. So let's say you're creating like, I don't know, Llama 3.1 vision, just for example, right? And you're using Llama 3.1 as the text part and then some other vision encoder in conjunction with it. You cannot regress the base capability of Llama 3.1. Otherwise, it's not a good model, obviously. So in this report, we present Qwen3VL and its advances in both general purpose and advanced applications. Built on the Qwen3 series, we instantiate 4 dense models, 2, 4, 8, and 32B, and 2 mixture of expert models, 30B, A3B, 235B, and A22B, each trained with a context window of up to 256K tokens to enable long context understanding. By optimizing the training corpus and training strategy, we preserve the underlying LLM's language proficiency, so that's a good thing. They preserve the language stuff, vision language training, and thereby substantially improving the overall capability. We release both non-thinking and thinking variants. The latter demonstrates, the thinking variant demonstrates significantly stronger multimodal reasoning capabilities, achieving superior performance on complex reasoning tasks. We first introduced the architectural improvements, which span 3 components. First, enhanced positional encoding. In Qwen 2.5 VL, we use MROPE as a unified positional encoding scheme for text and vision. We observed that chunking the embedding dimensions into temporal with T, horizontal H, and vertical groups induces an imbalanced frequency spectrum and hampers long video understanding. We therefore adopt an interleaved MROPE that distributes T, H, and W uniformly across low and high frequency bands, yielding more faithful positional representations. 2. Deep stack for cross-layer fusion. To strengthen vision language alignment, we incorporate the pioneering deep stack mechanism. Visual tokens from different layers of the vision encoder are routed to corresponding LLM layers. So I guess the tokens of the vision part of it, they are not being sent as one, but probably across the appropriate layers on the LLM side via lightweight residual connections, enhancing multi-level fusion without introducing extra long context length. 3. Explicit video timestamps. We replace the absolute time alignment via positional encoding used in Qwen 2.5 VL with explicit timestamp tokens to mark frame groups, providing a simpler and more direct temporal representation. In addition, on the optimization side, we move from a per sample loss to a square root normalized per token loss, which better balances the contributions of text and multimodal data during training. To build a more capable and robust vision language foundation model, we overhauled our training data in terms of quality, diversity, and structure. Key upgrades include enhanced caption supervision, expanded omni recognition and OCR coverage, normalized grounding with 3D and spatial reasoning, and new corpora for code, long documents, and temporal grounded video. We further infuse chain of thought reasoning and high quality diverse GUI agent interaction data to bridge perception, reasoning, and action. I really like this last part here because that's like in line of what I'm doing day to day as a hobby and work. Together, these innovations enable stronger multimodal understanding, precise grounding, and tool augmented intelligence. Our training pipeline consists of 2 stages, pre-training and post-training. Pre-training proceeds in 4 phases. A warm-up of alignment phase that updates only the merger, the vision language projection layers, while keeping the rest of the model frozen, followed by a full parameter training with progressively larger context windows at 8K, 32K, and 256K sequence lengths. Post-training comprises of 3 phases. First, simplifies fine-tuning on long chain of thought data, knowledge distillation from stronger teacher models, and 3, reinforcement learning. The above innovations equip Qwen3 VL with strong capabilities not only as a robust vision language foundation model, but also as a flexible platform for real-world multimodal intelligence, seamlessly integrating perception, reasoning, and action across diverse application domains. In the following sections, we present the model architecture, the training framework, and extensive evaluations that demonstrates its consistent and competitive performance on text vision and multimodal reasoning benchmarks. 2. Model architecture. Following Qwen 2.5 VL, Qwen3 VL adopts a 3-module architecture comprising a vision encoder. So first is a vision encoder, an MLP-based vision language merger, and a large language model, LLM. Figure 1 depicts the detailed model structure. So here we go. Here is so here's the language, the vision, and then I think this is the merger, most likely. Okay, is it? Looks like it. Okay, well, we can see here. Okay, large language model. Qwen3 VL is instantiated in 3 dense variants, okay, like we said before, 2B, 4B, 8B, 32B, and 2 MOE variants, 30B, A3B, and 235, A22B. All built upon Qwen3 backbones. The flagship model, Qwen3BL 235B A22B, has 235 billion total parameters with 22 billion parameters activated per token. Okay, so let's read the figure 1 first. Figure 1, the Qwen3 VL framework integrates a vision encoder and a language model decoder to process multimodal inputs, including text, images, and video. So let's see. Images, video, image. Okay, so we receive all this. It goes into the vision encoder, and I think it gets interleaved with all the pictures are first, and then video, and then I guess text is coming after this. Huh. Okay. The vision encoder is specifically designed to handle dynamic native resolution visual inputs, mapping them to vision tokens of variable length. To enhance perceptual capability and preserve rich visual information, we incorporate the pioneering deep stack mechanism, which injects visual tokens from multiple layers of the vision encoder into the corresponding layers of the LLM. So this is the deep stack part right here. All the tokens of the vision parts are interleaved with the LLM stuff. Furthermore, we adopt interleave envelope to encode positional information for multimodal inputs with a balanced frequency spectrum and introduce text-based timestamp tokens to more effectively capture the temporal structure of video sequences. So basically, going back to the the 235 A22B variant in the model, it outperforms most VLMs across a broad set of multimodal tasks and surpasses its only text counterpart on the majority of language benchmarks. So it is the VLM version of Qwen3 235B A22B surpasses the original text only version. Okay, so what's the vision encoder? The vision encoder. We utilize the SIGLIP2 architecture as our vision encoder and continue training it with dynamic input resolutions. So that's like the secret sauce or the special thing about these Qwen3 VL models is that they accept dynamic uh, input resolution, meaning that the images are not resized. They are like they can be of any size pretty much, and the model will take it just fine. So yeah, they're initialized from pre-trained checkpoints. To accommodate dynamic resolutions effectively, we employ 2D rope to and interpolate absolute position embeddings based on the input size, following the methodology of comp. Specifically, we default to the siglip2, I think just shaped optimized 400 million variant, and use siglip2 large and use the siglip2 large 300 million variant for small scale LLMs, the 2B and the 4B. MLP based vision language merger, as in Qwen 2.5 VL. We use a 2-layer MLP to compress 2x2 visual features from the vision encoder into a single visual token, aligned with the LLM's hidden dimension. Additionally, we deployed specialized mergers to support the deep stack mechanism, and the details which are fully described in section 2.2. Interleave mRope. Qwen2 VL introduced mRope to model positional information for multimodal inputs. In its original formulation, the embedding dimensions are partitioned into temporal T, horizontal H, and vertical W subspaces, each assigned distinct rotary frequencies. This results in an imbalanced frequency spectrum, which subsequent studies have shown to degrade performance on long video understanding benchmarks. To address this, we redesigned the frequency allocations by interleaving the TH and W components across the embedding dimensions. This ensures that each spatial temporal axis is universally represented across low and high frequency bands. The resulting balanced spectrum mitigates the original spectral bias and significantly improves long-range positional modeling for video. Not sure what that means, but that's the reason why I'm reading this, so I can pick out what I don't know and go deeper. Deep Stack. We draw inspiration from Deep Stack and inject visual tokens into multiple layers of the LLM. Unlike the original Deep Stack approach, which stacks tokens from multi-scale visual inputs, we extend Deep Stack to extract visual tokens from the intermediate layers of the vision transformer, and this design preserves rich visual information ranging from low to high level representations. Specifically, as illustrated in Figure 1, we select features from 3 distinct levels of the vision encoder. Subsequently, we dedicated vision language merger modules project these multi-level features into visual tokens, which are then added directly to the corresponding hidden states of the first 3 LLM layers. Video timestamp. In Qwen 2.5 VL, a time-synchronized variant of mRope is employed to endow the model with temporal awareness. However, we identify 2 key limitations of this approach. First, by tying temporal position IDs directly to absolute time, the method produces excessively large and sparse temporal position IDs for long videos, degrading the model's ability to understand long temporal contexts. 2. Effective learning under this scheme requires extensive and uniformly distributed sampling across various frame rates, significantly increasing the cost of training data construction. To address these issues, we adopt a textual token-based time encoding strategy, wherein each video temporal patch is prefixed with a timestamp expressed as a formatted text string. For example, less than 3.0 seconds. Furthermore, during training, we generate timestamps in both seconds and hours, minutes, seconds formats to ensure the model learns to interpret diverse timecode representations. Although this approach incurs a model's increase in context length, it enables the model to perceive temporal information more effectively and precisely, thereby facilitating time-aware video tasks such as video grounding and dense captioning. Pre-training. Training recipe. We first enhance the vision encoder by conducting continuous training with dynamic resolutions based on the pre-trained siglip2 model. Okay, so training with images with dynamic resolutions. Okay, fine. The overall Qwen3 VL model adopts a 3-module architecture comprising this vision encoder, an MLP-based vision language merger, and a Qwen3 large language model backbone. Building on this architecture, our pre-training methodology is systematically structured into 4 distinct stages, designed to progressively build capabilities from basic alignment to long context understanding. An overview of these stages is presented in Table 1. So stage 1, just do aligning, train the merger, the vision language merger, on 67 billion tokens. Everything else is frozen. Context length 8K. Then multimodal pre-training, train everything with 1 trillion tokens, but only at 8K. And then long context pre-training, so 32K with 1 trillion tokens. And then finally, ultra long context with 100 billion tokens, 256K tokens. Stage 0, vision language alignment. The initial stage, as 0 focuses on efficiently bridging the modality gap between the vision encoder and the LLM. So yeah, in the beginning, when you create a VLM and you just like attach a vision encoder with the LLM, both are like kind of disconnected, and you kind of want to make them both aware of each other. So you have to kind of like train them, and you train the merger part of it, I guess, is like to make sure that whatever the vision encoder outputs, it's something that the LLM will also like be familiar with. Crucially, only the parameters of the MLP merger are trained during this phase, while both the vision encoder and LLM backbone remain frozen. We utilize a curated dataset of approximately 67 billion tokens, consisting of high-quality image caption pairs, visual knowledge collections, and optical character recognition data. All training is conducted with a sequence length of 8K. This alignment first approach establishes a solid foundation for cross-modal understanding before proceeding to full parameter training. Multimodal pre-training. Following this initial alignment, stage 1 transitions to full parameter multimodal pre-training. In this phase, we unfreeze all model components, the vision encoder, the merger, and the LLM for joint end-to-end training. The model is trained on a massive and diverse dataset of approximately 1 trillion tokens. To maintain the LLM's strong language abilities, the data mixture is composed of vision language VL data and text-only data. The VL portion is rich and varied, adding interleaved image text documents, visual grounding tasks, and visual question answering VQA data from STEM domains, and a small amount of video data to introduce temporal understanding. The sequence length remains at 8K. And then finally, you have, well, not finally, but second to finally, I think what really matters, because I think most LLMs break down at the 32K context anyway. So stage 2, long context pre-training. Stage 2 aims to significantly extend the model's contextual processing abilities. A key change in this stage is the quadrupling of the sequence length to 32K, while all model parameters continue to be trainable. Training is conducted on a dataset of approximately 1 trillion tokens with an adjusted data mixture to support long context tasks. The proportion of text-only data is increased to bolster long-form text comprehension, while the remaining VL data incorporates a significantly larger volume of video and agent-oriented instruction following data. This stage is critical for enabling the model to process and reason over longer videos and complex multi-step tasks. Ultra-long context adaptation. The final stage, S3, is a specialized phase designed to push the model's context windows to its operational limits. Here, we dramatically increase the sequence length to 256K. The model is trained on a more focused 100 billion token dataset, specifically curated for this purpose. The data is also composed of text-only data and VL data with a strong emphasis on long video and long document understanding tasks. This final adaptation solidifies Qwen3 VL's proficiency in processing and analyzing extremely long sequential inputs, a key capability for applications like comprehensive document analysis and lengthy video summarization. Pre-training data. Image caption and interleaved text image data. To build a robust foundation model for general-purpose vision language understanding, we significantly expand and refine 2 core data modalities: image caption pairs and interleaved text image sequences. Our strategy emphasizes high-quality, diverse, and semantically rich multimodal grounding, supported by purpose-built models and rigorous filtering pipelines. image caption data. We curate a large-scale corpus of contemporary, predominantly Chinese English multilingual image text pairs from web sources and apply a multi-stage refinement pipeline centered on a specialized Qwen 2.5 VL32B model, fine-tuned for recaptioning. This model leverages the original raw text associated with each image to generate more comprehensive, fluent, and fine-grained captions, enriching descriptions of visual elements, for example, object attributes, spatial layouts, and contextual semantics, while simultaneously improving the linguistic quality and informativeness of the textual component. Deduplication is performed exclusively on the recaptioned text using semantic similarity metrics, ensuring removal of redundant examples without sacrificing visual diversity. To further enhance coverage of underrepresented concepts, we apply clustering over visual embeddings to identify sparse regions in the data distribution and perform targeted augmentation. The result is a high fidelity caption dataset that balances scale, diversity, and description granularity. Interleaved text image data. We collect diverse real-world multimodal documents sourced from recent Chinese and English websites. All documents undergo domain classification using a lightweight Qwen-based scorer fine-tuned for fine-grained domain identification. They're training models to not only do captioning, but they're also doing it for classifying a specific domain so that they can organize their data a bit. Based on validation experiments across domains, we systematically exclude harmful or low-value categories such as advertisements, promotional content, and clickbait, using the same efficient scorer to filter out undesirable samples. For book scale interleaved data, we employed a fine-tuned Qwen 2.5 VL7B model to perform high accuracy multimodal processing, specifically extracting and aligning text with embedded figures, diagrams, and photographs. To enable ultra-long context modeling, we construct a specialized subset by merging consecutive pages into sequences of up to 256K tokens, preserving natural page order and multimodal coherence. During pre-processing, we enforce strict quality controls. For pure text or low alignment segments are removed. For ultra-long book sequences, we require a minimum page count and a minimum image-to-text ratio to ensure meaningful visual textual interaction throughout the context. This yields a clean and diverse and layout-aware interleaved corpus optimized for both grounded understanding and long-range multimodal reasoning. Knowledge. Okay, world knowledge. World knowledge is essential for multimodal large language models, MLLM, to achieve robust visual understanding, grounded reasoning, and entity-aware generation across diverse downstream tasks. To equip Qwen3VL with a comprehensive grasp of both real-world and fictional concepts, we construct a large-scale pre-training dataset centered on well-defined entities spanning more than a dozen semantic categories, including animals, plants, landmarks, food, and everyday objects such as vehicles, electronics, and clothing. Real-world entities follow a long-tailed distribution. Prominent concepts appear frequently with high-quality annotations, while the majority are rare. To address this imbalance, we adopt an importance-based sampling strategy. High prominence entities are sampled more heavily to ensure a sufficient learning signal, while low prominence entities are included in smaller proportions to maintain broad coverage without overwhelming the training process. This approach effectively balances data quality, utility, and diversity. All retained samples undergo a multi-stage refinement pipeline. In addition to standard filtering for noise and misalignment, we replace original or sparse captions such as generic alt text with richer LLM-generated descriptions. These enhanced captions not only identify the main entity, but also describe its visual attributes, surrounding context, spatial layout, and interactions with other objects or people, thereby providing more complete and grounded textual representation. Together, these efforts yield a knowledge-rich, context-aware, and discrimination-focused training signal that significantly enhances Qwen3VL's ability to recognize, reason about, and accurately describe visual concepts in real-world scenarios. Okay, OCR, document parsing, and long document understanding. OCR. To enhance OCR performance on real-world images, we curate a dataset of about 30 million in-house collected samples using a coarse-to-fine pipeline. This pipeline refines OCR annotations by integrating pseudo-labels from OCR specialized models with refinements from Qwen 2.5 VL without any human annotation, expanding beyond the 10 languages supported by Qwen 2.5 VL, excluding Chinese and English. We incorporate an additional 29 languages, synthesizing approximately 30 million high-quality multilingual OCR samples and curating over 1 million internal real-world multilingual images. Document parsing. For document parsing, we collect 3 million PDFs from the Common Crawl, evenly distributed across 10 document types, 300K samples each, along with 4 million internal documents. An in-house layout model first predicts the reading order and bounding boxes for textual and non-textual regions. Qwen 2.5 VL72B then performs the region-specific recognition. The outputs are reassembled into position-aware layout aligned parsing data. To establish robust parsing across the heterogeneous formats, we designed a unified annotation framework supporting 2 representations. Qwen VL HTML, which includes fine-grained and element-level bounding boxes, and then Qwen VL Markdown, where only images and tables are localized with the tables encoded in LaTeX. We construct a large-scale synthetic HTML corpus with precise annotations and systematically convert it to a markdown format. To further improve model generalization, we generate pseudo-labels on extensive collections of real documents and filter them for quality. The final training set combines synthetic and high-quality pseudo-label data to enhance both scalability and robustness. Long document understanding. To enhance the model's ability to understand multi-page PDFs, often spanning dozens of pages, we leverage a large-scale corpus of long document data. First, we synthesize the long document parsing sequences by merging single-page document samples. In each sequence, multiple pages are placed at the beginning, followed by their corresponding text derived from OCR or HTML parsing. Second, we construct long document visual question answering data. Specifically, we sample high-quality multi-page PDFs and generate a diverse set of VKOS samples that require the model to reason across multiple pages and heterogeneous document elements such as charts, tables, figures, and body text. We carefully balance the distribution of question types and ensure that supporting evidence draws from a wide range of modalities and layout components, thereby promoting robust, grounded, and multi-hop reasoning over extended contexts. Visual grounding is a fundamental capability for multimodal models, enabling them to accurately identify, interpret, and localize a wide spectrum of visual targets from specific objects to arbitrary image regions. In Qwen3 VL, we systematically enhance grounding proficiency and support 2 grounding modalities, bounding boxes and points. So what visual grounding is the linkage between the knowledge of spatial awareness of the model to whatever's in the, like, being able to link objects in the image at certain positions. And I would say that that's like in a precise way too, to the point where you can draw bounding boxes in image around specific objects. And in order to do that, you need to have some sort of awareness of like where the coordinates, right, where you are at, and that requires spatial awareness. These representations allow for precise and flexible interpretation of image content across diverse scenarios and downstream tasks. In addition, we extend the grounding capacity of the model to support counting, enabling quantitative reasoning and visual entities. In the following, we briefly describe the data construction pipelines for grounding and counting. Box-based grounding. We begin by aggregating widely used open source datasets, including COCO, Object365, Open Images, and RefCOCO. To further enrich data diversity, we developed an automated synthesis pipeline that generates high-quality object annotations across a broad range of scenarios. This pipeline operates in 3 stages. Object candidates are extracted from unlabeled images using Qwen 2.5 VL. These candidates are localized and annotated using both open vocabulary detectors, specifically Grounding Dino, and Qwen 2.5 VL. The resulting annotations undergo quality assessment, with low confidence or inaccurate ones systematically filtered out. Through this approach, we constructed a large-scale, highly diverse box-based grounding dataset spanning a wide variety of visual contexts and object categories. Point-based grounding. To ensure robust point-based grounding, we curated a comprehensive dataset combining publicly available and synthetically generated pointing annotations. It integrates three sources: public pointing and counting annotations from Pixmo, object grounding data derived from public object detection and instance segmentation benchmarks, high precision pointing annotations generated by a dedicated synthesis pipeline designed to target fine-grained image details, and fine counting. Building upon the grounding data, we curated a high-quality subset to form the basis of our counting dataset, which includes three distinct task formulations: direct counting, box-based counting, and point-based counting. Collectively, these three task types constitute a comprehensive counting dataset. Different from Qwen3 VL, we adopt a normalized coordinate system scaled to the range of 0 to 1000. In this version, this design improves robustness to variations in image resolution and aspect ratios across diverse inputs, while also simplifying post-processing and enhancing the usability of predicted coordinates in downstream applications. Okay, so coordinate system, no matter how many pixels or how big your image is, it's always going to be normalized to 0 to 1000. So it operates in this space. So I think if you were to ask for bounding boxes from the model, it will always give you like coordinates in this range. So to facilitate sophisticated interaction with the physical world, Qwen3 VL is designed with a deep understanding of spatial context. This enables the model to interpret spatial relationships, infer object affordances, and perform action planning and embodied reasoning. It can also estimate the 3D spatial positions of objects from a single monocular image. To support these capabilities, we created two comprehensive datasets focused on spatial understanding and 3D grounding. Spatial understanding. Beyond localizing objects, Qwen3 VL is trained to reason about spatial relationships, object affordances, and feasible actions in 2D scenes, capabilities essential for embodied AI and interactive applications. To this end, we construct a specialized dataset that goes beyond standard grounding by incorporating, first, relational annotations. Examples of this be like a picture of a cup to the left of the laptop, or two, affordance tables. Is this graspable, pressable, or sittable? And action condition queries that require planning. What should I move first to reach the book behind the monitor? These samples are derived from both curated real-world scenes and synthetically generated layouts, with natural language queries automatically generated via templated and LLM-based methods to ensure diversity and complexity. Critically, all spatial references are expressed relative to other objects or scene frames, rather than absolute coordinates, encouraging robust relational reasoning. This training enables Qwen3 VL to not only answer where questions, but also how and what can be done, forming a foundation for agentic interaction with visual environments. 3D grounding. To further enhance the model's ability to understand the physical world from images, we constructed a specialized pre-training dataset for 3D visual grounding. We sourced data from public collections of diverse indoor and outdoor scenes and reformulated it into a visual question answering format. Each sample consists of 1. A single view camera image, 2. A natural language referring expression, and 3. The corresponding 9D DOF 3D bounding box annotations in the structured JSON format specifying the object's spatial position and semantic label. As the 3D bounding boxes are derived from multiple sensors and data sources, they exhibit varying camera intrinsic parameters and inherent noise. To this end, we filter out heavily occluded and inaccurate labels and follow Omni3D to unify all data into a virtual camera coordinate system. We also synthesize a large corpus of descriptive captions to create rich textual queries for 3D grounding. These descriptions go beyond naming the object's categories to include detailed attributes, layout arrangements, spatial location, visual affordances, and interactions with surrounding objects, yielding more fine-grained and grounded referring expressions. Code. So we enhance the Qwen3 VL series with dedicated coding capabilities by incorporating 2 categories of code-related data into the training corpus, enabling the model to read, write, and reason about programs in both text-only and visually grounded contexts. Text-only coding. We reused the extensive code corpus from the Qwen3 and Qwen3 Coder series. This large-scale dataset spans a wide range of programming languages and domains, including software development, algorithmic problem-solving, mathematical reasoning, and agent-oriented tasks, and establishes the model's foundational understanding of code syntax, arithmetic logic, and general-purpose program generation. Multimodal coding. To address tasks requiring both visual understanding and code generation, we curate data for a diverse suite of multimodal coding tasks. In this dataset, sourced from both open source datasets and internal synthesis pipelines, it teaches the model to jointly understand visual inputs and generate functional code. The data covers several key tasks, including converting UI screenshots into responsive HTML CSS, generating editable SVG codes from images, and solving visual programming challenges, answering multimodal coding questions, and transcribing visual representations, flowcharts, diagrams, and LaTeX equations, into their respective code or markup. This novel data mixture enables Qwen3 VL to act as a bridge between visual perception and executable logic. Video. The video comprehension capabilities of Qwen3 VL have been substantially advanced, enabling robust modeling of temporal dynamics across frames, fine-grained perception of spatial relationships, and coherent summarization of ultra-long video sequences. This enhancement is underpinned by a data processing pipeline featuring 2 principal innovations: temporal-aware video understanding, dense caption synthesis. For long video sequences, we employ a short to long caption synthesis strategy to generate holistic, time-stamped, interleaved, and temporal coherent story-level descriptions. Leveraging in-house captioning models, we further produce fine-grained annotations that jointly capture event-level temporal summaries and segment-specific visual details. Spatiotemporal video grounding. We curate and synthesize large-scale video data annotated at the levels of objects, actions, and persons to strengthen the model's spatiotemporal grounding capabilities, thereby improving its capacity for fine-grained video understanding. Video data balancing and sampling. Source balancing. To ensure data balance and diversity, we assemble a large-scale dataset encompassing various video sources, including instructional content, cinematic films, egocentric recordings, etc. Dataset balance is achieved through systematic curation, guided by metadata such as video titles, duration, and categorical labels. 2. Length adaptive sampling. During pre-training stages, we dynamically adjust the sampling parameters such as frames per second and maximum number of frames according to different sequences length constraints. This adaptive strategy mitigates information loss associated with suboptimal sampling practices, for example, overly sparse frame selection or excessively low spatial resolution, thus preserving visual details and optimizing training efficiency. Science, technology, engineering, mathematics, STEM. Multimodal reasoning lies at the heart of Qwen3 VL, with STEM reasoning constituting its most essential part. Our philosophy follows a divide-and-conquer strategy. We first develop fine-grained visual perception and robust linguistic reasoning capabilities independently, and then integrate them in a synergistic manner to achieve effective multimodal reasoning. Visual perception data. We developed a dedicated synthetic data generation pipeline that constructs geometric diagrams through programmatic or code-based rendering. Using this pipeline, we generate 1 million point grounding samples, such as intersection points, corners, and centers of gravity, and 2 million perception-oriented visual question and answering pairs targeting fine-grained visual understanding of diagrams. To obtain high-fidelity textual descriptions, we further implemented a 2-stage captioning framework. in an initial generation phase followed by rigorous model-based verification. Both stages employ ensembles of specialized models to ensure accuracy and descriptive granularity. This process yields a comprehensive dataset of 6 million richly annotated diagram captions spanning diverse STEM disciplines. Multimodal reasoning data. The majority of our multimodal reasoning data consists of over 60 million K-12 and undergraduate level exercises, meticulously curated through a rigorous cleaning and reformulation pipeline. During quality film filtering, we discard low quality items. We discard low quality items, including those with corrupted images, irrelevant content, or incomplete or incorrect answers. During the reformulation stage, we translate exercises between Chinese and English and standardize the format of answers such as step-by-step solution lists, mathematical expressions, and symbolic notations to ensure consistency and uniform presentation. Regarding the long COT, I think chain of thought, regarding long chain of thought problem-solving data, we synthesize over 12 million multimodal reasoning samples paired with images. To ensure continuity and richness of the reasoning process, we utilize the original rollouts generated by a strong reasoning model. To guarantee data reliability and applicability, each sample's reasoning trajectory undergoes vigorous validation, combining rule-based checks and model-based verification, and any instances containing ambiguous answers or code switching are explicitly filtered out. Furthermore, to enhance reasoning quality, we retain only challenging problems via rejection sampling. Linguistic reasoning data. In addition to multimodal reasoning data, we also incorporate reasoning data from Qwen3 as multimodal reasoning capabilities are largely derived from linguistic reasoning competence. Agent. Ooh, this is a fun one. GUI. To endow Qwen3VL with agentic capability for autonomous interaction with graphical user interfaces, or GUIs, we curate and synthesize large-scale cross-platform data spanning desktop, mobile, and web environments. For GUI interface perception, we leverage metadata, parsing tools, and human annotations to construct tasks such as element description, dense captioning, and dense grounding, enabling robust understanding of diverse user interfaces. For agentic capability, we assemble multi-step task trajectories with a self-evolving trajectory production framework complemented by targeted human audits. We also carefully design and augment chain of thought rationales to strengthen planning, decision-making, and reflective self-correction during real-world execution. Function calling. For general function calling capabilities with multimodal contexts, we build a multimodal function calling trajectory synthesis pipeline. We first instruct capable models with images to generate user queries and their corresponding function definitions. We then sample model function calls with rationales and synthesize the function responses. This process is repeated until the user's query is judged to be solved. Between each step, trajectories can be filtered out due to formatting errors. Such a pipeline enables us to construct large-scale multimodal function calling trajectories from vast images without the need to implement executable functions. Okay, this is normal tool calling. Search. Among the general function calling capabilities, we regard the ability to perform searches as a key to facilitating knowledge integration for long-tail entities in real-world scenarios. In this case, we collect multimodal factual lookup trajectories with online image search and text tools, encouraging the model to perform searches for unfamiliar entities. By doing so, the model learns to gather information from the web to generate more accurate responses. Oh, didn't know that. Okay, post-training. Our post-training pipeline is a three-stage process designed to refine the model's instruction following capabilities, bolster its reasoning capabilities, and align it with human preferences. So this is after all that pre-training. This is where it becomes like a chat model. This becomes like a GUI agent. This becomes a lot of things. And I think they're just generalizing it to become a chat model. The specific data and methods for each stage are detailed in the subsequent sections. So they go through supervised fine-tuning, SFT, The first stage imparts instruction following abilities and activates latent reasoning skills. So this turns it into a chat app, or a chat model, that is. This is conducted in two phases: an initial phase at a 32K context length, followed by an extension to a 256K context window that focuses on long document and long video data. To cater to different needs, we bifurcate the training data into standard formats for non-thinking models and chain of thought formats for thinking models, the latter of which explicitly models the reasoning process. Strong to weak distillation. The second stage employs knowledge distillation, where a powerful teacher model transfers its capability to our student models. Crucially, we perform this distillation using text-only data to fine-tune the LLM backbone. This method proves highly effective, yielding significant improvements in reasoning abilities across both text-centric and multimodal tasks. Reinforcement learning. The final stage utilizes RL to further enhance model performance and alignment. This phase is divided into reasoning RL and general RL. We apply large-scale reinforcement learning across a comprehensive set of text and multimodal domains, including but not limited to math, OCR, grounding, and instruction following to improve finer-grained capabilities. Okay, cold start data, SFT data. What is cold start data? Our principal objective is to endow the model with the capacity to address a wide spectrum of real-world scenarios, building upon the foundational capabilities of Qwen 2.5 VL, which is proficient in approximately 8 core domains and 30 fine-grained subcategories. We have strategically expanded its functional scope. This expansion was achieved by integrating insights from a community feedback, academic literature, and practical applications, facilitating the introduction of novel capabilities. These include, but are not limited to, spatial reasoning for embodied intelligence, image-grounded reasoning for fine-grained visual understanding, spatio-temporal grounding in videos for robust object tracking, and the comprehension of long context technical documents spanning hundreds of pages. Guided by these target tasks and grounding in authentic use cases, we systematically curated the SFT dataset through the meticulous selection and synthesis of samples from open source datasets and resources. This targeted data engineering effort has been instrumental in establishing Qwen3 VL as more comprehensive and robust multimodal foundational model. Okay, so to develop this breadth, the data set comprises approximately of 1.2 million samples, strategically composed to foster robust multimodal capabilities. This collection is partitioned into unimodal and multimodal data, with 1/3 consisting of text-only entries and the remaining 2/3 comprising image-to-text and video-text pairs. The integration of multimodal content is specifically designed to enable the model to interpret complex real-world scenarios. To ensure global relevance, the dataset extends beyond its primary Chinese and English corpora to include a diverse set of multilingual samples, thereby broadening its linguistic coverage. Furthermore, it simulates realistic conversational dynamics by incorporating both single-turn and multi-turn dialogues, contextualized within various visual settings, from single image to multi-image sequences. Crucially, the dataset also features interleaved image-to-text examples engineered to support advanced agentic behaviors such as tool-augmented image search and visually grounded reasoning. This heterogeneous data composition ensures comprehensive coverage and enhances the dataset's representativeness for training generalizable and sophisticated multimodal agents. Given Qwen3 VL's native support for a 256K token context length, we employ a staged training strategy to optimize for computational efficiency. This strategy comprises two phases: an initial 1 epoch training phase with a sequence length of 32K tokens, followed by a second epoch for at the full 256K token length. During this latter stage, the model is trained on a curriculum that interleaves long context inputs with data sampled at the 32K context length. Their long context inputs include materials such as hundreds of pages of technical documents, entire textbooks, and video up to 2 hours in duration. The quality of training data is a critical determinant of the performance of vision language models. Datasets derived from open source and synthetic origins are often plagued by substantial variability and noise, including redundant, irrelevant, or low quality samples. To mitigate these deficiencies, the implementation of a rigorous data filtering protocol is indispensable. Accordingly, our data curation process incorporates a two-phase filtering pipeline: query filtering and response filtering. Query filtering. In this initial phase, we leverage Qwen 2.5 VL to identify and discard queries that are not readily verifiable. Queries with ambiguous instructions are minimally revised to enhance clarity while preserving the original semantic intent. Furthermore, web source queries lacking substantive content are systematically eliminated. Crucially, all remaining queries undergo a final assessment of their complexity and contextual relevance, ensuring only appropriately challenging and pertinent samples are retained for the next stage. Response filtering. This phase integrates two complementary strategies. Rule-based filtering. A set of predefined heuristics is applied to eliminate responses exhibiting qualitative deficiencies, such as repetition, incompleteness, or improper formatting. To maintain semantic relevance and uphold ethical principles, we also discard any query response pairs that are off topic or possess the potential to generate harmful content. Model-based filtering. The dataset is further refined by employing reward models derived from the Qwen 2.5 VL series. These models conduct a multidimensional evaluation of multimodal question-answer pairs. Specifically, answers are scored against a range of criteria, including correctness, completeness, clarity, and helpfulness. For vision-grounded tasks, the evaluation places special emphasis on verifying the accurate interpretation and utilization of visual information. And C, this model-based approach enables the detection of subtle issues that typically elude rule-based methods, such as inappropriate language mixing or abrupt stylistic shifts. This multidimensional filtering framework ensures that only data meeting stringent criteria for quality, reliability, and ethical integrity is advanced to the SFT phase. Okay, so here's like my takeaway so far of all this is that the way you process your data and the way and your data set quality is pretty much a lot of how you can achieve state-of-the-art performance for any model. It's not about the model architecture, what it is, but not mostly that. It's also like not about how many GPUs you have. It's not about like your hyperparameters. It's really a lot of it seems to have to do with your dataset quality, and I think this is the reason why they put so much effort into creating a very good dataset. Okay, so water. Long chain of thought and cold start data. The foundation of our thinking models is a meticulously curated long chain of thought, COT, cold start data set, engineered to elicit and refine complex reasoning capabilities. This dataset is built upon a diverse collection of queries spanning both pure text and multimodal data, maintaining an approximate 1-to-1 ratio between vision language and text-only samples to ensure balanced skill development. The multimodal component, while covering established domains such as visual question answering, VQA, optical character recognition, OCR, 2D, 3D grounding, and video analysis, places a special emphasis on enriching tasks related to STEM and agentic workflows. The strategic focus is designed to push the model's performance on problems requiring sophisticated multi-step inference. The pure text portion closely mirrors the data used for Qwen3, featuring challenging problems in mathematics, code generation, and logical reasoning in general STEM. To guarantee high quality and an appropriate level of difficulty, we implement a rigorous multi-stage filtering protocol. So first is going to be difficulty curation. We selectively retain instances where baseline models exhibit low pass rates or generated longer and more detailed responses. This enriches the dataset with problems that are genuinely challenging for current models. So they keep all the really hard stuff. Multimodal necessity filtering for vision, language, mathematics problems. We introduce a critical filtering step. We discard any samples that our Qwen3 30B no-think model could solve correctly without access to visual input. This ensures that the remaining instances genuinely necessitate multimodal understanding and are not solvable via textual cues alone. Response quality control. Aligning with the methodology of Qwen3, we sanitize the generated responses. For queries with multiple candidate answers, we first remove those containing incorrect final results. Subsequently, we filter out responses exhibiting undesirable patterns such as excessive repetition, improper language mixing, or answers that show clear signs of guessing without sufficient reasoning steps. This stringent curation process yields a high-quality, challenging dataset tailored for bootstrapping advanced multimodal reasoning. Strong to weak distillation. We adopt the strong to weak distillation pipeline as described in Qwen3 to further improve the performance of lightweight models. This distillation process consists of two main phases. Off-policy distillation. In the first phase, outputs generated by teacher models are combined to provide response distillation. This helps lightweight student models acquire fundamental reasoning abilities, establishing a strong foundation for subsequent on-policy training. On-policy distillation. In the second phase, the student model generates the responses based on the provided prompts. These on-policy sequences are then used for fine-tuning the student model. We align the logics predicted by the student and teacher by minimizing the KL divergence. Reinforcement learning. Reasoning reinforcement learning. We train models across a diverse set of text and multimodal tasks, including mathematics, coding, logical reasoning, and visual grounding and visual puzzles. Each task is designed so that solutions can be verified deterministically via rules or code executors. Data prep. We curate training data from both open source and proprietary sources and apply rigorous pre-processing and manual annotation to ensure high-quality reinforcement learning queries. For multimodal queries, we use a preliminary checkpoint of our most advanced vision language model, Qwen3 VL235BA22B, to sample 16 responses per query. Any query for which all responses are incorrect are discarded. We then run preliminary RL experiments per task to identify and remove data sources with limited potential for improvement. This process yields approximately 30,000 RL queries, covering a variety of text and multimodal tasks. For training each model, we sample 16 responses for all queries and filter out easy queries whose pass rate exceeds 90%. We shuffle and combine task-specific datasets to construct mixed task batches, ensuring consistent predefined ratio of samples per task. The ratio is determined through extensive preliminary experiments. So reward system. We implement a unified reward framework that delivers precise feedback across all tasks. The system provides shared infrastructure, data preprocessing, utility functions, and a reward manager to integrate multiple reward types. While the core reward logic is implemented per task, we use task-specific format prompts to guide model outputs to the required formats and therefore do not rely on explicit format rewards. To mitigate code switching, we apply a penalty when the response language differs from the prompt language. RL algorithm. We employed SAPO, a smooth and adaptive policy gradient method for RL training. SAPO, something preference optimization, delivers consistent improvements across diverse text and multimodal tasks and across different model sizes and architectures. General reinforcement learning. The general reinforcement learning stage is designed to enhance a model's generalization, capabilities, and operational robustness. To this end, we employed a multitask RL paradigm where the reward function is formulated based on a comprehensive set of tasks from the SAT phase, including VQA, image captioning, OCR, document parsing, grounding, and clock recognition. The reward mechanism is structured to optimize two principal dimensions of model performance. I love how they say clock recognition. I think I heard that models like to this day with like vision language models still struggle in reading hands of a clock. Maybe that's what they're referring to. Okay, anyway, instruction following. This dimension evaluates the model's adherence to explicit user directives. It assesses the ability to handle complex constraints on content, format, length, and structured outputs, JSON, ensuring the generated response precisely matches the user requirements. Reference alignment. For open-ended or subjective queries, this dimension aligns the model's outputs with human preferences by optimizing for helpfulness, factual accuracy, and stylistic appropriateness. This fosters a more natural and engaging user interaction. Furthermore, this stage acts as a corrective mechanism to unlearn strong but flawed knowledge priors ingrained during SFT. We address this by introducing specialized verifiable tasks designed to trigger these specific errors, such as counterintuitive object counting and complex clock time recognition. This targeted intervention is designed to supplant erroneous priors with factual knowledge. Another critical objective is to mitigate inferior behaviors like inappropriate language mixing, excessive repetition, and formatting errors. However, the low prevalence of these issues makes general RL a sample inefficient correction strategy. To overcome this, we curate a dedicated dataset at this stage. This dataset isolates prompts known to elicit such undesirable behaviors. This focused training enables the application of targeted high-frequency penalties, effectively suppressing these residual errors. Feedback for the RL process is delivered via a hybrid reward system that combines two complementary approaches. Rule-based rewards. This approach provides unambiguous, high-precision feedback for tasks with verifiable ground truths such as format adherence and instruction following. By using well-defined heuristics, this method offers a robust mechanism for assessing correctness and effectively mitigates reward hacking, where a model might exploit ambiguities in a learned reward function. Model-based rewards. This method employs Qwen3 VL72B instruct or Qwen3 as sophisticated judgers. These judge models evaluate each generated response against a ground truth reference, scoring its quality across multiple axes. This approach offers superior flexibility for assessing nuanced or open-ended tasks where strict rule-based matching is inadequate. It is particularly effective at minimizing false negatives that would otherwise penalize valid responses with unconventional formatting or phrasing. Wow, there's a lot of phases here. I used to think that we just do like a complete pass of training on a model and it'd be good to go, but this is so complicated in that they split their training process into different sessions. Thinking with images. Inspired by the great prior works on thinking with images, we endow Qwen3 VL with similar agentic capabilities through a two-stage training paradigm. In the first stage, we synthesize a cold start agentic dataset comprising approximately 10K grounding examples, primarily simple two-turn visual question answering tasks such as attribute detection. We then perform supervised fine-tuning, SFT, on Qwen2.5 VL32B to emulate the behavior of a visual agent. Think, act, analyze feedback, and answer. To further enhance its reasoning capabilities, we apply multi-turn tool-integrated reinforcement learning. In the second stage, we distilled the trained Qwen2.5 VL32B visual agents from the first stage to generate a larger, more diverse dataset of approximately 120,000 multi-turn agentic interactions spanning a broader range of visual tasks. We then apply a similar cold start SFT and tool-integrated RL pipeline, now using both distilled and synthesized data for the post-training of Qwen3 VL. The multi-turn tool-integrated RL procedure is nearly identical across both stages, differing only in the underlying data. During RL, we employ three complementary reward signals to encourage robust tool-mediated reasoning. Accuracy or answer accuracy reward leverages Qwen332B to measure whether the final answer is correct. Multi-turn reasoning reward leverages Qwen 2.5 VL72B to evaluate whether the assistant correctly interprets tool or environment feedback and arrives at the answer through coherent step-by-step reasoning. Tool calling reward encourages appropriate tool usage by comparing the actual number of tool calls to an expert estimated target. This target is determined offline by Qwen 2.5 VL72B based on task complexity. Early experiments reveal a tendency for models to degenerate into making only a single tool call to hack the first two rewards, regardless of task demands. To mitigate this, we explicitly incorporate the tool calling reward to promote adaptive tool exploration aligned with task complexity. Infrastructure. We trained the Qwen3 VL series models on Alibaba's cloud PAI Lingjun AI computing service, which provides the high-performance computing power required for the compute-intensive scenarios such as AI and high-performance computing. During the pre-training phase, the system employs a hybrid parallelism strategy built upon the Megatron LM framework, integrating tensor parallelism and pipeline parallelism, PP, context parallelism, CP, expert parallelism, EP, and 0-1 data parallelism, DP. This configuration achieves a fine-grained balance among model scale, computational load, and communication overhead, enabling high hardware utilization and sustaining both high throughput and low communication latency, even at scales of up to 10,000 GPUs. For local deployment and performance evaluation, we adopt deployment strategies based on either a VLLM or SGLang. VLLM utilizes page attention to enable memory-efficient management and high-throughput inference, while SGLang excels at structured generation and handling complex prompts. Together, these backends provide efficient inference and evaluation with stable, efficient, and flexible model inference capabilities. Evaluation. General visual question answering. To comprehensively assess the general visual question answering VQA capabilities of the Qwen3 VL series, we conduct extensive evaluations on a diverse set of benchmarks, including MMBench v1.1, Real-World QA, MMStar, and Simple VQA. As detailed in Table 2, Table 3, and Table 4, the Qwen3 VL family demonstrates robust and highly competitive performance across a wide spectrum of model sizes, from 2 billion to 235 billion parameters. In the comparison of thinking mode, Qwen3 VL 235A22B thinking achieves the highest score of 78.7 on MMStar. Gemini 2.5 Pro's thinking mode delivers the best overall performance, but Qwen3 VL 235A22B thinking is not far behind. In the non-reasoning mode comparison, Qwen3 VL 235B A22B Instruct obtains the highest scores on MMBench and Real-World QA with 89.3 and 88.9 and 79.2 respectively. In the experiments with medium-sized models, Qwen3 VL32B thinking achieves the highest scores on MMBench and Real-World QA with 89.5, 89.5, and 79.4 respectively. Notably, Qwen3 VL32B Instruct even outperforms the thinking variant on Real-World QA, scoring 79. The scalability of the Qwen3 VL series is evident in the strong performance of our smaller models. Specifically, the largest model, Qwen3 VL-AB. I guess. I guess the largest small model. Specifically, the largest model, Qwen3 VL-AB, achieves the highest performance across all 5 benchmarks. For example, on MMBench EN, the score in thinking mode increases from 79.9 for the 2B model to 85.3 for the 8B model. A similar upward trend is observed in other benchmarks, such as MMStar, where the score rises from 68 2B thinking to 75.3 8B thinking. Multimodal reasoning. We evaluate the Qwen3 VL series on a wide range of multimodal reasoning benchmarks, primarily focusing on STEM-related tasks and visual puzzles. including MMMU, MMMU Pro, MathVision, MathVision Wild, MathVista, WeMath, MathVerse, Dynamath, MathVR, Logic Vista, Visual Puzzles, VLM are blind, Zero Bench, and VisuLogic. As shown in Table 2, the flagship Qwen3 VL model demonstrates outstanding performance across both non-thinking and thinking models. Notably, Qwen3 VL235B A22B Instruct achieves the best performed or best reported results among non-thinking or low-thinking budget models on multiple benchmarks, including MathVista Mini, MathVision, MathVerse Mini, Dynamath, Zero Bench, VLMs are blind, VisuLogic, Visual Puzzles Direct, and while Qwen3 VL235B A22B Thinking achieves state-of-the-art results on MathVista Mini, MathVision, MathVerse Mini, Zero Bench, Logic Vista, and VisuLogic. Among medium-sized models, as shown in Table 3, Qwen3 VL32B demonstrates significant advantages, consistently outperforming Gemini 2.5 Flash and GPT-5 Mini. Compared to the previous generation Qwen 2.5 VL72B model, so that's the biggest one I think before, the medium-sized Qwen3 VL model has already surpassed it on reasoning tasks. This highlights significant progress in VLMs. Additionally, our newly introduced Qwen3 VL30B A3B MOE model also delivers competitive results. Among small-sized models, we compare Qwen3 VL2B, 4B, 8B against GPT-5 Nano with results presented in Table 4. The 8B variant maintains a clear advantage overall, while the 4B model achieves the highest scores on Dynamath and VisuLogic. Notably, even the smallest 2B model exhibits strong reasoning capabilities. Alignment and subjective tasks. The ability to follow complex user instructions and reduce potential image-level hallucinations is indispensable for current large language models or large vision language models. Let me read that again. The ability to follow complex user instructions and reduce potential image-level hallucinations is indispensable for current large vision language models. We assess our models on 3 representative benchmarks: MMMT Bench, Hallution Bench, and MIA Bench. MMMT Bench is a multi-turn LLM as a judge evaluation benchmark for testing multimodal instruction-tuned models. Hallution Bench aims at diagnosing image context reasoning and poses great challenges for current VLMs. MIA Bench is a more comprehensive benchmark to evaluate models' reactions to users' complex instructions. For example, creative writing with character limit and compositional instructions. As shown in Table 2, our flagship Qwen3 VL235B A22B model consistently outperforms other closed-source models. On Hallution Bench, our thinking version surpasses Gemini 2.5 Pro and GPT-5 and Claude Opus 4.1 by 3.0, 1.0, and 6.3 points respectively. On MIA Bench, Qwen3 VL235B A22B Thinking achieves the best score overall across all the other models, showing our superior multimodal instruction following ability. We also investigate detailed subtask results of MIA Bench. Our model overtakes GPT-5 High Thinking version by 10 and 5 points in math and textual subtasks of MIA Bench respectively. The same trend can be observed on our smaller size models like Qwen3 VL30B A3B and Qwen3 VL32B, where they overtake other models with comparable sizes. Our 2B, 4B, 8B series also performs well and shows a negligible drop, especially on MIA Bench. Okay, text recognition and document understanding. We compare the Qwen3 VL series with other models of comparable size on document-related benchmarks, including OCR, document parsing, document question answering, QA, and document reasoning. We evaluate our flagship model, Qwen3 VL235B A22B, against the state-of-the-art VLMs on the benchmarks listed in Table 2. On OCR-focused parsing benchmarks, including CCOCR and OmniDoc Bench, as well as comprehensive OCR benchmarks such as OCR Bench and OCR Bench v2, the Qwen3 VL235B A22B instruct model let's take a look at this later. Establishes a new state-of-the-art, marginally outperforming its thinking counterpart, Qwen3 VL235B A22B thinking, on OCR-related visual question answering VQA benchmarks that require both OCR capability and keyword search, such as DocVQA and InfoVQA, AI2D, ChartQA, and Chartarchive. Description subset, both the instruction and thinking variants achieve comparable performance, demonstrating consistently strong results across these tasks. Notably, on the reasoning subset of Chartarchive, which demands deep chart comprehension and multi-step reasoning, the thinking variant surpasses the instruct version and ranks second only to GPT-5 thinking and Gemini 2.5 Pro thinking. Okay, let's look at some of the data here. Okay, so performance of Qwen3 VL235B A22B and top-tier models on visual benchmarks. The highest scores of the reasoning and non-reasoning models are shown in bold and underlined, respectively. So the highest scores for reasoning are in bold, non-reasoning are underlined, respectively. Results marked with an asterisk, a star, are sourced from the technical report, plus denotes the results with tool use. Okay, so there are a lot to do tool use in some of these. Okay, so let's first take a look at some of what these benchmarks are. So what is MMMU Pro? So let's go to this guy and just ask, what's the benchmark MMMU Pro? And let's just do like some light thinking. Oh, I guess I don't, because I want to see like what that even looks like. Help us kind of learn and visualize. Because we've been reading it, but not really sure what it is. After cutoff. Let's just look it up. MMU Pro benchmark, a massive multidiscipline, multimodal understanding and reasoning benchmark for expert AGI. Okay. What is it? Okay, so I guess these are some examples. So among the following harmonic intervals, which one is constructed incorrectly? So then I guess it's multiple choice. The graph shown is compiled from data collected from Gallup. Okay, image 1. Find the probability that the selected emotional health index is between 80 and 80.5 and 82. Oh, I see. So it is just like learning how to link visually the question and an image associated with it. Okay, so that's the benchmark. Interesting. Leaderboard GPT 5.1. Let's see. Human expert. Okay, human expert medium. GPT 5 with thinking is the best. So Qwen3 is pretty up there too, right here. Dots VLM, surprisingly. Cool. I wonder if there's another Qwen model here, like a smaller one up here. Qwen, no, just the bigger Qwen2 VL models are here. It's not until where we get to, I guess this is not benchmarked here. Okay, that's fine. And then what do we have? Another one, I guess, is general VQA. Let's see what that has. So Bench, EN benchmark. So this one is based off of paper, I guess. I want an example. Okay, so example of this would be How many apples are there in the image? A, 4, B, 3, C, 2, D, 1. So 1, 2, 3, 4. Okay. So these are the types of benchmarks basically that they do on these vision language models. And as you can see, I think they're starting to get saturated. Like here for this one's like 96.5, 97.1. And yeah, since like even all these models are actually doing relatively well on these benchmarks at this point. I think specifically the hardest one is probably the spatial understanding. I think VLMs tend to do really bad on spatial stuff. So I'm not surprised that these are lower. Um, let's see, for multimodal coding, Cloud Opus, I was expecting that to be very, very strong, but turns out that not really. And then agent stuff. This is like stuff I love is Screenshot Pro, OS World G. So yeah, it does really well on these. Cool. And then oh, here's a medium sized one. That's interesting. All right, cool. So only the medium. But what is screen spot? Okay, not that far off. Spatial understanding is probably gonna be even worse. Let's see. Right here. Yeah, we're scoring into below 50s on some of them now. And then let's take a look at the small one. Oh, we're good here. Okay. Furthermore, among smaller sized variants in the Qwen3 VL series, both Qwen3 VL30B-A3B models and Qwen3 VL32B models consistently outperform Gemini 2.5 Flash and GPT-5 Mini across most evaluation metrics, as shown in Table 3. Even the compact dense models Qwen3 VL8B, Qwen3 VL4B, and Qwen3 VL2B demonstrate remarkably competitive performance on OCR parsing, visual question answering, and comprehensive benchmark suites as detailed in Table 4. This highlights the exceptional efficiency and strong scalability of the Qwen3 VL architecture across model sizes. In this version of the Qwen3 VL, we have placed particular emphasis on enhancing its ability to understand long documents. As reported in Table 2, in a comparison within the flagship models on the Long benchmark, our Qwen3 VL235B A22B achieves overall accuracy of 57%, 52% under instruct thinking settings, showcasing the state-of-the-art performance on the long document understanding task. Beyond its strong performance on established benchmarks, we have also made substantial strides in multilingual support. This represents a major expansion from the 10 non-English Chinese languages supported by Qwen 2.5 VL to 39 languages in Qwen 3 VL. We assess this expanded capability on a newly constructed in-house dataset. As illustrated in Figure 2, the model's accuracy surpasses 70%, a threshold we consider practical for real-world usability on 32 out of 39 languages tested. This demonstrates that the strong OCR capabilities of Qwen3 VL are not confined to a handful of languages, but extend across a broad and diverse linguistic spectrum. 2D and 3D grounding. In this section, we conduct a comprehensive evaluation of the Qwen3 VL series on both 2D and 3D grounding related benchmarks and compare the models with state-of-the-art models that possess similar capabilities. We evaluate Qwen3 VL's 2D grounding capabilities on the referring expression comprehension benchmarks RefCoco and the open vocabulary object detection benchmark ODIN W and the counting benchmark CountBench. For ODIN W13, we adopt mean average precision MAP as the evaluation metric by setting confidence scores to 1. To ensure comparability with conventional open set object detection specialist models, we provide all dataset categories simultaneously within the prompt during evaluation, as shown in Table 2. Our flagship model Qwen3 VL235B A22B demonstrates outstanding performance and achieves state-of-the-art SOTA results across 2D grounding and counting benchmarks. Notably, it achieves 48.6 MAP on ODIN W, demonstrating strong performance in multi-target open vocabulary object grounding. Detailed results for our smaller scale variants, which also exhibit competitive performance in 2D visual grounding, are presented in Tables 3 and 4 respectively. Okay, so let's take a look at this. Oh, so this is the smaller one. Okay, I was looking for this. So I'm curious, like how much different is the 4B and 8B on these, right? So they're actually not far apart. In fact, if you take a look at instruct, the instructs are very close to each other. On STEM puzzles, it's within like 1 or 2%, except for some reason this one is it's a huge difference. But overall, like it's compelling like enough for me to try out the 4B instead. I usually like to use the 8B, but the 4B is really good. And it competes quite well. In fact, I think it surpasses GPT-5 Nano here. But for 2D, 3D grounding, that's interesting. They're about the same, pretty much. In fact, for whatever reason, in terms of counting, the 4B model does better than the 8B and the non-thinking mode. Huh, interesting. And then let's look at the multimodal agent one. Yeah, here we go. Yeah, 4B seems to be very good too with that, except for the OS World and the Windows AA. But again, not terrible for, I mean, like it's half the parameters, but it's not like half the performance here. It's good. Okay. Moreover, in this version of Qwen3 VL, we enhance its spatial perception capabilities for 3D object localization. We evaluate the Qwen3 VL series against other models of comparable scale on Omni 3D, a comprehensive benchmark comprising datasets such as AR kit scenes, HyperSim, and Sun RGBD. We employ mean average precision MAP as our evaluation metric. Each input is an image text pair consisting of the image and textual prompt specifying the object category. To ensure a fair comparison with existing VLMs, we set the IOU threshold to 0.15 and report MAP at 0.15 on the Omni 3D test set, with detection confidence fixed at 1.0. As shown on Table 2, our flagship Qwen3 VL235B A22B model consistently outperforms other closed-source models across multiple datasets. Specifically, on the Sun RGBD dataset, the Qwen3 VL235B A22B thinking variance surpasses the performance of Gemini 2.5 Pro by 5.2 points. Our smaller scale variants, Qwen3 VL30B A3B, 32B, 8B, 4B, and 2B, also exhibit remarkably competitive performance in 3D object grounding with detailed results provided in tables 3 and 4 respectively. Fine grain perception. We measure the model's fine grain perception abilities or capabilities on 3 popular benchmarks. The Qwen3 VL series demonstrates a substantial leap in fine grain visual understanding compared to its predecessor, Qwen 2.5 VL72B. Notably, Qwen3 VL235B A22B achieves the state-of-the-art performance across 3 benchmarks when augmented with tools, reaching 93.7 on V-star, and then 85.3 on HR Bench 4K, and 82.3 on HR Bench 8K. This consistent outperformance highlights the effectiveness of architectural refinements and training strategies introduced in Qwen3 VL, particularly in handling high-resolution inputs and subtle visual distinctions visual distinctions critical for fine-grained perception tasks. I noticed that yes, it can learn this pretty well from my fine-tuning experience, and I'm very impressed by its ability to see very subtle things. Second, and perhaps more surprisingly, the performance gains from integrating external tools consistently outweigh those from simply increasing model size. For example, within the Qwen3 family, the absolute improvement by adding tools is consistently 5 points across V star. These findings reinforce our conviction that scaling tool-integrated agentic learning in multimodality is a highly promising path forward. Multi-image understanding. Beyond single-image grounded dialogue evaluation, advancing VLMs to handle multi-image understanding is of significant value. This task requires higher-level contextual analysis across diverse visual patterns, enabling more advanced recognition and reasoning capabilities. To this end, we nourish Qwen3 VL with comprehensive cross-image pattern learning techniques, including multi-image referring grounding, visual correspondence, and multi-hop reasoning. We evaluated Qwen3VL on two prominent multi-image benchmarks, Blink and Mirror Bench. As shown in Table 2, Qwen3VL demonstrates overall superiority in multi-image understanding compared to other leading LVLMs. Specifically, Qwen3 VL235B A22B Instruct achieves performance comparable to state-of-the-art models such as Gemini 2.5 Pro, while Qwen3 VL235B A22B Thinking attains a remarkable leading score of 80.1 on Mirror Bench, surpassing all other models. Nice. Embodied and spatial understanding. For embodied and spatial understanding, Qwen3VL's performance is rigorously benchmarked against leading state-of-the-art models using a challenging suite of benchmarks: ERQA, VSI Bench, Embed Spatial, Ref Spatial, and RoboSpatial Home. Across these benchmarks, the model showcases exceptional capabilities, rivaling the performance of top-tier models like Gemini 2.5 Pro, GPT-5, and Cloud Opus 4.1. This success is largely driven by the model's profound spatial understanding, which stems from its training on high-resolution visual data with fine-grained pointing, relative position annotations, and QA pairs. This capability is clearly validated by its strong results on Embed Spatial, Ref Spatial, and RoboSpatial Home, where Qwen3 VL235B A22 B achieved scores of 84.3, 69.9, 73.9 respectively. Moreover, its embodied intelligence is significantly enhanced through the integration of pointing, grounding, and spatio-temporal perception data during training, leading to top-tier scores of 52.5 on ERQA and 60.0 on VSI Bench for Qwen3 VL235B A22B. Okay, so video understanding. Benefiting from the scaling of training data and key architectural enhancements, Qwen3VL demonstrates substantially improved video understanding capabilities. In particular, the integration of interleaved mRope and insertion of textual timestamps and scaling temporally dense video captions collectively enable the Qwen3 VL8B variant to achieve performance competitive with the significantly larger Qwen2.5 VL72B model. We conduct a comprehensive evaluation across a diverse set of video understanding tasks encompassing general video understanding with video MME and VBench, temporal video grounding with Charades STA, and video reasoning with video MMMU and MMVU, and long-form video understanding with LVBench, LVU, and in comparison with state-of-the-art proprietary method models, including Gemini 2.5 Pro, GPT-5, Cloud Opus 4.1, Qwen3VL demonstrates competitive and, in several cases, superior performance. In particular, our flagship model, Qwen3 VL235B A22B Instruct, achieves performance on par with leading models such as Gemini 2.5 Pro with a thinking budget of $128 and GPT-5 minimal on standard video understanding benchmarks. By extending the context window to 256K tokens, it further attains or even surpasses Gemini 2.5 Pro on long video evaluation tasks, most notably on MLVU. Regarding evaluation details, we impose a cap of 2048 frames per video for all benchmarks, ensuring that the total number of video tokens did not exceed 224K. The maximum number of tokens per frame was set to 768 for video MMMU and MMVU, and 640 for all other benchmarks. Additionally, videos from Charades STA were sampled at 4 frames per second, while a rate of 2 FPS was used for all other benchmarks. For video MMMU, we employed a model-based judge for evaluation as rule-based scoring proved insufficiently accurate. Okay. It is worth noting that our comparison cannot guarantee full fairness due to resource and API limitations, which constrain the number of input frames used during evaluation. 512 for Gemini 2.5 Pro, 256 for GPT-5, and 100 for Cloud Opus 4.1. Agents. We evaluate UI perception with UI or GUI grounding tasks using ScreenSpot Pro, OS World G, and assess decision-making abilities through online environment evaluations, Android World, OS World. For GUI grounding, Qwen3 VL235A22B achieves the state-of-the-art performance across multiple tasks, covering interactive interfaces on desktop, mobile, and PC, and demonstrating exceptionally strong UI perception capabilities. For online evaluations, Qwen3 VL32B scores 41 on OS World and 63.7 on Android World, which surpasses the current foundation VLMs. Qwen3 VL demonstrates exceptionally strong planning, decision-making, and reflection abilities as a GUI agent. Furthermore, smaller Qwen3 VL models have demonstrated highly competitive performance on these benchmarks. Text-centric tasks. To comprehensively evaluate the text-centric performance of Qwen3 VL, we adopt automatic benchmarks to assess model performance on both instruct and thinking models. These benchmarks can be categorized into the following key types: knowledge, MMLU Pro, MMLU Redux, and GPQA, Super GPQA, and then reasoning, we have AIM 25, HMMT 25, Live Bench, and then we have Code Live Bench V6, CF Eval, OJ Bench, and Alignment Task IF Eval. Arena Hard V2, Creative Writing V3, Writing Bench, and then BFCL V3, Tau2 Retail, Tau2 Airline, Tau2 Telecom, Multilingual, Multi-F, MMLU Pro X, Include, and Polymath. So this is the LLM part, I think. Okay, so evaluation settings for Qwen3 VL instruct models, including 235B, A22B, 32B, 30B, A3B. We configure the sampling hyperparameters with temperature 0.7, top P 0.8, top K 20, and presence penalty as 1.5. As for the small instruct models, including 8B, 4B, and 2B, we set the temperature to 1, top P 1, top K 40, and presence penalty 2.0. We set the max output length to 32K tokens. For Qwen3 VL thinking models with mixture of experts MOE architecture, we set the sampling temperature to 0.6, top P to 0.95, and top K to 20. For dense thinking models, we set temperature to 1.0, top P, top P 0.95, top K 20, and additionally apply a presence penalty of 1.5 to ensure greater output diversity. We set the max output length to 32K tokens, except for AIM 25, HMMT 25, and Lightcode Bench V6, where we extend the length to 81,920 tokens to provide sufficient thinking space. The detailed results are as follows. Okay, so here it is. Interesting. It's competing with Cloud Opus and DeepSeek V3, and the really big models actually don't do that bad in comparison. In fact, AIM 25 is very good. I'm guessing it's, I don't know, benchmax maybe? How could it be that good? That's interesting. So, yeah. All right. Yeah. Okay, so details. Qwen3 VL235B A22B. We compare our flagship model Qwen3 VL235B A22B with the leading instruct and thinking models. For Qwen3 VL235B and A22B instruct, we take Qwen3 235B A22B instruct 2507, DeepSeek V30324, and Cloud Opus 4 without thinking as the baselines. For Qwen3 VL235B A22B thinking, we take Qwen3 235B A22B thinking 2507 and OpenAI O3 medium, Cloud Opus 4 with thinking as baselines. We present the evaluation results in Table 5 and Table 6. So this one was Table 5, and the next one to follow will most likely be Table 6. So from Table 5, Qwen3 VL235B A22B instruct achieves competitive results comparable to even surpassing the other leading models, including DeepSeek V30324 and Cloud Opus 4 without thinking. And our previous flagship model, Qwen3 235B A22B instruct 2507, particularly Qwen3 VL235B A22B instruct exceeds other models on reasoning demand tasks. mathematics and logic, mathematics and coding, for example. It is worth noting that DeepSeek v3 0324 and Qwen3 235b 822b Instruct 2507 are LLMs, while Qwen3 VL 235b 822b Instruct is a VLM, which can process visual and textual tasks. This means that Qwen3 VL 235b Instruct has achieved the integration of visual and textual capabilities. For Qwen3 VL 235b 822b Thinking, it also achieves competitive results with other leading thinking models. Qwen3 VL 235b 822b Thinking exceeds OpenAI O3, Medium, Claude Opus 4 with thinking on AIM 25 and Live Code Bench v6, which means Qwen3 VL 235b 822b Thinking has better reasoning ability. Whew. Okay. Qwen3 VL32b 30b A3b. We compare our Qwen3 VL32b and Qwen3 VL30b A3b models with their corresponding text-only counterparts, namely Qwen3 32b and Qwen3 30b A3b and Qwen3 30b A3b 2407. We present the evaluation results in Table 7 and Table 8. Okay, so from Table 7 for Instruct models, Qwen3 VL32b and Qwen3 VL30b A3b show significant performance improvements compared to the Qwen3 32b and Qwen3 30b A3b on all the benchmarks. Qwen3 VL30b A3b achieves comparable or even better results compared to Qwen3 30b A3b 2507, particularly AIM and HMMT. From Table 8 for thinking models, Qwen3 VL32b and Qwen3 VL30b A3b surpasses the baselines in most of the benchmarks. Qwen3 VL30b A3b also shows comparable performance compared with Qwen3 30b A3b 2507. Okay. Yeah, AIM is pretty high up there. I'm surprised that Claude Opus isn't smarter. Huh. Okay. So how about the smaller ones? Qwen3 VL8B4B2B, we present the evaluation results of Qwen3 VL2B, Qwen3 VL4B, and Qwen3 VL8B in Table 9 and Table 10. For Qwen3 VL2B and Qwen3 VL8B, we compare them with the Qwen3 1.7b and Qwen3 8b. For Qwen3 VL4b, we compare it with Qwen3 4b and Qwen3 4b 2507. Overall, these edge side models exhibit impressive performance and outperform baselines. These results demonstrate, okay, so where are we at? Oh, right here. So again, they're all like not too different from each other, so it's very compelling to use. So the Qwen3 architecture in general seems to be very good. Except, yeah, I think at a certain point you just fall off in intelligence after a certain number of parameters. 2B is really just a 1.7b with the vision encoder on top of it in total. Okay, anyway, the efficacy of our strong to weak distillation approach, making it possible for us to build the lightweight models with remarkably reduced cost and efforts. Okay. Great. Okay, ablation study. And this, I love these because it just shows you what they like did to like just take things out to see if it would affect performance. And it's always curious to see because then you start to learn like what's not needed, even though you might think that it's needed. Okay, so vision encoder. We conduct comparative experiments against the original SIGLIP2, as showed in Table 11, in zero-shot evaluation at the clip pre-chaining stage. Qwen3 Vision Transformer maintains competitive performance on standard benchmarks while achieving substantial gains on OmniBench, our in-house holistic evaluation suite designed to assess world knowledge, integration under diverse and challenging conditions. Furthermore, when integrated with the same 1.7b Qwen3 language model and trained for 1.5 trillion tokens, Qwen3 Vision Transformer consistently outperforms the SIGLIP2 based baseline across multiple key tasks and remains significantly ahead on OmniBench demonstrating its superiority and effectiveness as a stronger visual backbone. Oh, that's interesting because I always had this assumption that the Qwen3 vision encoder was Siglip 2, but they kept saying deep stack, and that's the vision transformer that they're using. So here, I think they're testing the difference, like if we were to use the vision transformer versus the Siglip 2 encoder, like how well are we going to how much better are we going to do? So ablation on Qwen3 Vision Transformer, we compare the performance metrics of Qwen3 VIT and Siglip 2 during the clip pre-training stage. So just the performance of training the vision encoder, and further evaluate their downstream performance in the vision language modeling stage when paired with the same 1.7B Qwen3 language model. So they created like a Qwen3 2B VL, whatever, with this. Okay. Um, so yeah, it looks like I would say not exactly like a huge difference. Maybe for this one, but overall, like I think it's very minor. I think that's like kind of hinting something about vision coders is that I think they can only get so good, maybe. Deep stack. Maybe this is what boosts it. So we conduct an ablation study to verify the effectiveness of the deep stack mechanism. As demonstrated in Table 12, the model equipped with deep stack achieved an overall performance gain across various benchmarks, strongly affirming its effectiveness. This gain is attributed to deep stack's ability to integrate rich visual information, which effectively boosts the capability in fine-grained visual understanding, such as on the InfoVQA and DocVQA benchmarks. So ablation on deep stack. We conduct the ablation study on the deep stack using an internal 15B A2B LLM with all experiments pre-trained on 200 billion tokens. We directly evaluate these pre-trained models on the validation sets without any post-training. Okay. What is this? So needle and haystack performance heat map for Qwen3VL 235B, A22B instruct across varying video durations and needle positions. Each cell shows accuracy for locating and answering questions about the inserted needle frame. Oh, okay. So needle and haystack. To evaluate the model's capability in processing long context inputs, we construct a video needle in a haystack evaluation on Qwen3 VL235B A22B instruct. In this task, a semantically salient needle frame containing critical visual evidence is inserted at varying temporal positions within a long video. The model is then tasked with accurately locating the target frame from the long video and answering the corresponding question. During evaluation, videos are uniformly sampled at 1 FPS and frame resolution is dynamically adjusted to maintain constant visual token budget. As shown in Figure 3, the model achieves a perfect 100% accuracy on videos up to 30 minutes in duration, corresponding to the context length of 256K tokens. Remarkably, even when extrapolating to sequences of up to 1 million tokens, approximately 2 hours of video, via a yarn-based positional extension, the model retains a high accuracy of 99.5%. These results strongly demonstrate the model's powerful long sequence modeling capabilities. In conclusion, in this work, we present Qwen3VL, a state-of-the-art series of vision language foundation models that advances the frontier of multimodal understanding and generation. By integrating high-quality multimodal data iteration and architectural innovations such as enhanced interleaved MROP, deep stack vision language alignment, and text-based temporal grounding, Qwen3VL achieves unprecedented performance across a broad spectrum of multimodal benchmarks while maintaining strong pure text capabilities. Its native support for 256K token interleaved sequences enable robust reasoning over long complex documents, image sequences, and videos, making it uniquely suited for real-world applications demanding high-fidelity cross-modal comprehension. The availability of both dense and mixture experts variants ensures flexible deployment across diverse latency and quality requirements, and our post-training strategy, including non-thinking and thinking modes. Looking forward, we envision Qwen3VL as a foundational engine for embodied AI agents capable of seamlessly bridging the digital and physical worlds. Such agents will not only perceive and reason over rich multimodal inputs, but also execute decisive, context-aware actions in dynamic environments, interacting with users, manipulating digital interfaces, and guiding robotic systems through grounded and multimodal decision making. So yeah, this is like a hint saying that okay, the priority now or like the hot thing will be agentic, like visual agentic work. Really, I think it's really cool. I think that's the future, like robots and like you know software automation visually. Future work will focus on extending Qwen3 VL's capabilities towards interactive perception to augmented reasoning and real-time multimodal control, with the ultimate goal of enabling AI systems that learn, adapt, and collaborate alongside humans in both virtual and physical domains. Additionally, we are actively exploring unified understanding generation architectures, leveraging visual generation capabilities to elevate overall intelligence further. By openly releasing the entire model family under the Apache 2.0 license, we aim to catalyze community-driven innovation towards the vision of truly integrated multimodal AI agents. Wow. Okay. So list of contributors, references. Okay, a lot here. We'll just slowly encounter them, I guess. And then evaluation prompts. Okay, so yeah. Okay, so evaluation prompts. Oh, grounding. Okay. What else? UMU. Yeah, that's it. We read an entire technical report, word for word. So yeah, I personally learned a little bit, and I have a lot of things that I don't know. So it's going to be worth exploring further. Thanks for that.